Hello, everybody. It is May 1st, and we are continuing our study of gases. And our focus today for this lesson is Table H from the reference tables, and it's all about vapor pressure of four liquids. So just taking a quick look at this table, we've got vapor pressure in kilopascals on the y-axis. We've got temperature in Celsius on the x-axis. And our four liquids are propanone, ethanol, water, and ethanoic acid. And I've actually got those molecular formulas or structural formulas present. Okay, so we have a ketone, an alcohol, water, and an acid. And we all learned about these very recently. Okay, so let's take a look here. This is a reminder from yesterday's lesson, and that is what a vapor is. A vapor is the gas phase of a substance that is liquid or solid at room temperature, and that vapor is that gas that forms above that liquid or solid. In these cases, these are all liquids, right? And they form a certain amount of vapor pressure above their liquid form in a closed system. So this lesson is really all about how we can use Table H to answer some questions about vapor pressure. So, first question, what is the vapor pressure in kilopascals of water at 100 degrees Celsius? Well, when we read across, we get to 100 degrees Celsius. We travel up, and you will note we intersect right here. We follow that dotted line, and we get 101.3 kilopascals. This happens to be the vapor pressure of water at sea level. Okay, let's look at another example. What is the vapor pressure in kilopascals of ethanoic acid at 120 degrees Celsius? So I read across 105, 110, 115, 120, 125. So there's 120. Reading up. Going across. We're roughly around here, which is 10, 20, 30, 40. So it's a little bit below or close to 110 kilopascals. So let's estimate that at about 108 kilopascals. Let's look at a few more examples. What is the vapor pressure in kilopascals of propanone at 75 degrees Celsius? We're going to go all the way up to the propanone line. Reading across, we are looking at approximately 180 kilopascals. Let's compare now the vapor pressure of the four liquids at 70 degrees Celsius. So we're going to keep the temperature the same, but let's look at what those relative vapor pressures are. So at 70, 55, 60, 65, 70. Okay, so at 70, we're looking at, for ethanoic acid, approximately 20-ish kilopascals. And water is approximately 30 kilopascals. And ethanol is approximately 70 kilopascals. And as we keep going up, propanone is approximately, looks like about 155 kilopascals. So when we compare them, propanone has the highest vapor pressure of the four liquids at a given temperature. That temperature is 70 degrees Celsius. then ethanol, then water, then ethanoic acid. Now, the most important question is why? Why would they have differing vapor pressures? The main answer is IMF. So going back only 2 units ago, the intermolecular forces of attraction will explain this. So when we look at these 4 examples, which of the 4 has the strongest attraction for itself? And looking here, in other words, which of these 4 has the strongest attraction that it will want to stay in liquid phase into? It will not want to leave and become that vapor phase if it has strong intermolecular forces of attraction. And if we look at that, the greatest IMF would have to have the lowest vapor pressure, right? And then that leads us to our answer. Out of these 4, ethanoic acid has the greatest intermolecular forces of attraction because it has the lowest vapor pressure. It's not going to want to become the gas phase as readily as propanone or the others. Okay, so as we rank the vapor pressure of these 4 liquids, this is the lowest vapor pressure going to the highest vapor pressure. And we can relate that vapor pressure to intermolecular forces of attraction, which can be related to polarity. So ethanoic acid is the most polar compound of all shown here. And it's most polar and therefore going to have very strong intermolecular forces of attraction, and therefore not want to become a vapor. So it's going to have a low vapor pressure. On the other hand, the least polar of these 4 compounds is propanone. It's got weaker intermolecular forces of attraction and therefore would have a higher vapor pressure. Other factors that would impact that vapor pressure of liquids would be the surface area of the liquid and the temperature. Okay, so let's go on to another example. First of all, liquids and boiling. Liquids will boil when the vapor pressure is equal to the pressure on the system. That's actually really important. The boiling of a liquid occurs when the vapor pressure above that liquid is equal to the pressure on the system. So let's look at some examples. Water boils at 100 degrees Celsius at sea level. And that's when you have 101.3 kilopascals. So as a reminder, right, we read up, we're right here. That is where water boils. But at 202.6 kilopascals, what temperature does water boil? 118 degrees Celsius. Let's look. Roughly a little over 200. Read over to the water. You're coming down here and you're approximately at 118 degrees Celsius. So the temperature at which a substance boils is impacted by the amount of pressure in the atmosphere. The higher the pressure, the higher the temperature of boiling. Lower pressure, lower temperature to boil. Okay, let's look at an example of Denver. I don't know if you've ever heard this, but Denver is called the Mile High City. Guess why? Its altitude is about a mile high, whereas most towns and cities in New York State are much closer to sea level. Denver has a higher altitude, and guess what? Its atmospheric pressure is only 84 kilopascals, whereas most of New York State is closer to 101 kilopascals because we're more like sea level, okay? So at what temperature will water boil when there's only 84 kilopascals? We could read across our table. 60, 70, about 84 is approximately here. We're gonna keep traveling across till we get to our water line. And we go down and we're looking at about 95, 96-ish. So if you live in Denver, water is going to boil at a lower temperature than it does here. It's kind of cool. So you could actually cook your spaghetti a little faster in Denver. Maybe I should move to Denver because I'm always hungry and I want to eat my spaghetti faster. This concludes my mini lesson on Table H. I hope you enjoyed it. Have a great day. Bye.